Okay, it's July 15, 2020. This is for Physics 5B. On the last email I sent out, which would have been last night by the time you're received, I think I made a mistake. So I thought that number 61 was on number 2. I'm getting so confused. 61 is on in lecture 3, so I've got in lecture 3 done. Number 2 was a long time ago. Okay, so anyway, this is on online assignment number 3, July 14th, 2020. And so you should have this up there. I think I just uploaded it now, or I could have uploaded it. It's there now. We can go look real fast. It's there now. So, okay, there's online worksheet number 3. Okay, these both have got a due date. Now expect an online worksheet number 4 to come up too, because we want to get into chapter 20 before the first exam. And then you've got, there's the worksheet. You can download it there. You can turn it in here. And then this PowerPoint here, number 19. If you haven't downloaded the newest version yet, this is the final newest version here. Okay, so everything is set here, I believe. And so let's go over to the PowerPoint. Now I believe this is where we left off last time. We had parallel plates. We had a charge we stuck in there, and you can see the charge is going to go. If it's a plus charge, it's going to feel a force in that direction. We talked about the work we had to do. We talked about the energy that we would have in the electric field and so on. Okay, so now remember we had the electric field due to a point charge. So electric field due to a point charge, just real quick, was up here. Electric field point charge equals Coulomb's constant times Q, okay, the charge we stuck into, the point charge, times the distance you are away from that point charge, okay? So you put a charge in there, you say, well, what's the electric field way out here away from this point charge, okay? Well, now we can figure out a way to figure out what the voltage is going to be away from that point charge. So here's that equation I just showed you, Coulomb's constant times Q divided by the distance from the point charge to the place you're interested in, trying to find the electric field for a point charge. But voltage equals the electric field times the distance, okay, from what R would be, okay? How far are you from that point times what the electric field is, okay? So that means KQ divided by R squared, that right there, times R, or the R up here cancels with one of the R's down here. We get the voltage equals KQ over R. So that would be the voltage out here. So the voltage obviously is going to decrease. Okay, here it's maximum voltage here. For example, it'll decrease as we go out. So that would be the voltage that would exist, the potential that would exist due to this point charge. So well, this is the one I gave you. Oh no, that's an old one. What was it's right over far. Here it is. Okay. So how far from a 1 microcoulomb point charge will the potential be 100 volts? At what distance will it be 2 times 10 to the 2 volts? Okay, well, we start off with that equation we just saw. To find the voltage some distance from some charge Q, we simply use this equation. But now what we want is how far from a point charge. So we have the voltage and we have Q. We have the charge and we have the voltage. Now you solve for R. You plug in your numbers and you get 90 meters. So if you had a 1.00 microcoulomb point charge, the potential would be 100 volts, okay, at a distance of 90 meters. Okay, and then at what distance will it be 2.00 times 10 to the 2 volts, or 200 volts? Twice as much. Okay, so it would be half the distance. Okay, so R equals the Coulomb's constant times the charge divided by what the voltage is at that point. And we're not here yet. Okay. Okay, now these are different electric field lines. So again, the electric field lines, they just like we've been talking about before, they start on the positive and they go towards the negative. We had that up here, okay? So they start on the positive, they go towards the negative. Here they are, start on the positive, they go towards the negative, okay? That's the way we draw the electric field lines. They're in the direction of the force that would be felt by a positive charge. The positive charge would feel a force away from positive and towards negative. So there's a positive charge, and so if you just had a point charge like this, okay, these guys, and then the voltages and so on. So since V equals K Q over R for a given point charge, it follows that the voltages, the same distance R from the charge would be equal. So in other words, we take this circle here. Okay, the voltage will be the same around there. Okay, for some reason I feel like I talked about this already. I went back and looked at the last video, and it looked like we stopped up there. Okay, anyway, maybe I imagined in my head. So now here, okay, the same voltage all the way around here because the R is the same. The only thing that's different in this equation is the R. The K is the same. It's the 9 times 10 to the 9th newtons meter squared per coulomb squared. The Q is the coulombs. That's this guy right here. We didn't change that. So anything that changes is the R. So if the R is the same, the voltage will be the same. Okay, these are called equipotential surfaces. Okay, so the electric field lines are perpendicular to the equipotential surfaces. The electric field lines radiate out from the charge perpendicular to the equipotential surfaces. Now here's some examples. This is something you would have done in the lab. I think at the end of the chapter 18, I had what kind of looks like what you would have done in the lab. Oh man, I have to write you guys some labs. That's something else I keep forgetting. I guess I got too much to do. All right. So anyway, here's what it would look like with 2 point charges. Okay, then here you've got this would be like the two. They're showing you basically the 2 charges. They got minus 10 and minus 10 here. So you got 2 minuses. So your equipotential surfaces would look like this. So you went around with a voltmeter. You see minus 5. Here's 10 volts. Here's 10 volts. These are the surfaces. So now you got this equipotential surface out here. That'd be minus 5 volts. And the way out here you get this thing looks like minus 2 volts. Now you draw your lines perpendicular. Now they go off the positive and towards the negative. So they end on the negative. But look how they're going. They're coming in like this. They're not going towards each other because these are both negatives. And then parallel plate. So this is 100 volts down to 0 volts. We've got 75 volts here, 50, and so on. These would be the equipotential surfaces. So you would have 2 parallel plates. You put a 100 volts on one, for example, 0 volts on the other. And you go along with the ohm meter or a voltmeter. You find all the little points where you have 75 volts, and you could like make that little curve right there. All the points of 50 volts and all the points of 25 volts. Then you can draw your electric field lines perpendicular to those. Okay, now for capacitors. Let's say we're going to hook a capacitor up to a battery. 2 uncharged parallel plates remain uncharged until the switch is closed. So right now we've got what we call an open switch. There's the switch right there. When we close it, and then boom, now these 2 are connected through this battery. Okay? 2 uncharged parallel plates remain uncharged until the switch is closed. When the switch is closed, there is a complete circuit, and the battery will pump electrons from the plate connected to the positive terminal to the plate connected to the negative terminal. So here we started pumping. We pumped an electron. Boom. It's nice and easy. That doesn't take much energy at all. It's nice and easy for the battery to do that. The switch is closed and uncharged parallel plates are connected through a battery. The battery, maintaining a voltage difference, removes negative charge electrons from the plate connected to the positive terminal. Here's the positive terminal. So it moved an electron from there and deposited it over here. It deposits them onto the plate. Hold on. Okay, and it deposits them onto the plate connected to the negative terminal. One plate acquires a charge of plus Q, and then the other plate acquires a charge of minus Q. These charges will not be very big at the beginning. Okay, they'll be rather small. But we keep hooking this setup up. The battery continues to pump electrons from the positive plate to the negative plate. As this happens, the charge of the plates increases, as does the electric field strength. Here, up here I only had one little line representing the electric field. Here I've got 2 of them. Okay, then we come down here. Now we've pumped even more. The battery continues to move electrons from one plate to the other, increasing both the charge on the plates as well as the strength of the electric field. Is there any limit to how large the charge can become and how strong the electric field can get? Well, yeah, there is a charge. You can only pump so many on there. These plates can only hold so much. So basically what we have here is a capacitor. This is a capacitor, okay? Increasing the charge on the plates increases the electric field between the plates. Therefore, the electric field is directly proportional to the charge on the plates. We also know that the voltage equals the electric field times the distance between the plates. So voltage is also directly proportional to the electric field. This means the voltage and the charge must also be directly proportional to each other. So we say the electric field, the greater the charge, the more charge we put on there, the greater the electric field between the plates is going to be. The more newtons per coulomb, more force per coulomb a charge in there will feel if you put more charge on there. And of course, Coulomb's law, the charge is going to repel and attract. Put more charge on there, you're going to increase that newtons per coulomb that a charge in the middle there would feel. But we know that the voltage is going to be equal to the electric field times the distance between the plates. So the greater we make the electric field, the greater the voltage is going to be between the plates. Therefore, V is proportional to E as well, and V is also proportional to Q. Okay, so we start pumping up here. See, we have little tiny bit of charge on here, a little electric field, and this could be a 12-volt battery. Maybe you only have 0.01 volts across here right now. So we'll increase the voltage across here, increase the strength of the electric field, increase the charges until we get to this point. So all of those are increasing as time goes by until we get the capacitor completely charged. We can't put any more charge on there. Capacitance directly relates to the maximum charge stored on a capacitor to the voltage that should be applied to it, not allied with it. Applied, it should be applied. I don't know how that happened. Okay, so the more voltage you apply, the more charge you're going to get. Okay, so we have this constant proportionality. It's a linear relationship, just like y equals mx with the point slope equation. Q, the charge on the capacitor, equals the capacitance of the capacitor times the voltage. All right. Charge Q equals capacitance C times voltage V. Q equals CV. Also, then capacitance equals charge per volt. That means what a capacitor can do is how many coulombs of charge can that capacitor store with this much voltage. So you have 10 volts. I say, okay, well, I've got 10 volts. I'm going to put it across this capacitor. How much charge can that capacitor store? Well, it depends on its capacitance. Okay, so capacitance is a measure of how much voltage the capacitor can hold per volt placed across it. And then you got all these different kind of capacitors. Some of these are evil. Back ages ago, like, I don't know, 1927, I used to work at this electronics place, and it was electronic. It was a Triad Systems Corporation. They made computers for basically the car parts companies or something like that. I never understood what that company did. It was a bad company. But anyway, I was just out of high school and I worked. Actually, I just got an A degree in electronics. And what they would do is they'd charge these capacitors up. So you'd have one plate that was all positive, the other plate that was all negative, and they'd take a pair of needle nose pliers or whatever, or they just hold it up here, and they'd toss it at somebody, and somebody wouldn't know any better, and they'd go to catch the damn thing, and it would like shock them right in the hand because it would discharge. All you had to do was get both these together, and it would discharge through your hand. So you get this big current going through your hand, and it would hurt. It would burn. That's what those guys did at Triad Systems Corporation. It was a bad company. Okay, the capacitance depends on the physical properties of the capacitor, the area of the plates, the distance between the plates, basically, and then dielectric. We're not gonna. I'm gonna like try to skip over dielectric, not just make the easy version of the dielectric idea. Okay, so now this is what the capacitance is equal to. So this is just a constant. It's permittivity of free space. It's just this number right here. Okay, I think you even have it on that. It's going to be here someplace. Permittivity of free space. Well, it's there. There it is. Okay, permittivity of free space. There it is, right there. So you've got it on your notes. I got to give you guys chapter 20 for this too pretty soon. All right. So permittivity of free space. That's all that is. It's just a constant. So the capacitance is directly related to the area and inversely related to the distance between the plates. Separation of the plates is D, and then surface area, that's A. That's going to be in meters squared. So the area in those other plates is in square meters, that's an area. The D is the distance between the plates, that's also going to be measured in meters. So C equals E0A over D. Capacitance is directly proportional to the area because the greater the area, the more charge the capacitor can store. We'll get more charge per volt if we got a greater surface area to put the charges on. Capacitance is inversely proportional to the distance because opposite charges apply an attractive force on one another. And the smaller the distance between them, the greater the force. In other words, Coulomb's, we have a Coulomb's thing here. We go back someplace where we got the plates charged up, like here. Okay, so basically these are kind of far apart maybe, right? So you put an electron there and it's kind of far apart, so there's an attractive force over here, but it's not very big. You make these plates smaller and smaller, okay, make them closer and closer together, then the force over here, the attractive force for these positives on these negatives is greater, and so you can get more electrons up there with a shorter distance. Okay, that's the idea there. So it's directly proportional to here we are. So it's directly proportional to the area, inversely proportional to the distance between the plates. You want the distance to be as small as possible and the area to be as big as possible. You can't make the distance too small, or you get the plates close to touching, and then basically you have electrons jumping across back on the other side, and then you don't have a charged capacitor anymore. Okay, now basically dielectric. This is the next thing you're thinking. What we do is we stick I thought I got a picture of that. Oops, I didn't. We would stick some material between there. Okay, stick some material between there, and we would increase the capacitance. And it's kind of interesting how it basically does something where the electric field is kind of weakened. And with the electric field weakened, you can stick more charges on there. It's a whole thing that we don't really need to go into the details of. But basically, here's the equation right here. Oops, went too far. We still have the original. See, there's the original right there. Okay. But that was for air or vacuum. See, for a vacuum, kappa, the dielectric constant, it's just 1. Or for air, which is what we're going to have between our capacitor plates, it's 1.00059. But you put some of these other ones in there, like fused quartz. You would increase the capacitance. It's physically the same capacitor, but instead of air, you went and slipped this fused quartz between there. Its capacitance goes up to 3.78, almost 4 times what it was before. If it was 10 farads before, now it'll be 40 farads just by slipping the stuff in there. So you got, now look at this one right here. It makes it go up 233 times. Don't know what the physics is. Water makes it go up 80 times. So you can have 2 parallel plates, and you can measure the charge across them. That's how many coulombs per volt that capacitor could charge. You go and stick water in there, and you multiply this number by 80. And now that's how much more charge it would be able to store. Okay, because the capacitance goes up. Remember, the capacitance goes up. Maybe people are forgetting this. Let's go back and look. Or it might be easier just to look here. Capacitance goes up. But remember, capacitance is Q over V. Q is CV. The voltage from the battery, that's not changing. But you increase the capacitance, that means you can store more charge on there. Okay, so we're done with that as far as I'm concerned. Maybe we can do some problems. We do some problems yet? Find the average. Yes. Okay. Okay, here we go. Find the charge stored on a 5.5 volt battery. It's a 5.5 volt battery is applied to an 8.00 picofarad capacitor. Yeah, farad is the units for capacitance. So picofarad will be 10 to the minus 12. See, micro is 10 to the minus 6, nano is 10 to the minus 9, pico is 10 to the minus 12. So the charge we can store is equal to the capacitance. This guy could store 8 times 10 to the minus 12 coulombs per volt. So it's a very small capacitor. It doesn't store very much. Put a whole volt across there, it can only store 8 picofarads of charge. I mean, you put 1 volt, it can only store 8 picofarads of charge across there. So we go our 8 times 10 to the minus 12 farads times, we actually have 5.5 volts we put across there, and we can get up to 44.0 picocoulombs. We can 44.0 times 10 to the minus 12 coulombs of charge. Okay, what is the capacitance of a parallel plate capacitor having plates of area 1.50 meters squared and are separated by 0.0200 millimeters of neoprene rubber? Okay, neoprene rubber was on the list. Neoprene rubber, there it was, 6.7. So all you need to do, there's your 6.7. That's a constant. We were told the plates were had an area of 1.50 meters squared, and the distance between them is 0.0200 millimeters, or 0.02 times 10 to the minus 3 meters. So you plug all that in, and you would have a 4.4 microfarad capacitor. With those physical properties, with that dielectric stuck into it, we would have a capacitor that could store 4.4 microcoulombs of charge for every 1 volt we put across it. What charge does it hold when 9 volts is applied to it? Well, this is basically, all of this probably works out to be, we'll see, you got, yeah, here we go. I don't know why I did, see, 4.5. Okay, I know why, because, see, here's the thing. This guy only has 2 digits of accuracy, so your answer should only have 2 digits of accuracy here. But here, you go ahead and go back to your 3 digits of accuracy and your 3 digits of accuracy, but then you have your answer at 2 digits, because remember, this guy here is still sticking you up with the 2 digits of accuracy. That's why 3 digits, and 2 digits there. So you simply take your capacitance times your voltage, and you can store 4.0 times 10 to the minus 5 coulombs of charge on this capacitor if you put 9 volts across it. Okay, this is one I never expected you to have to do, but like I told you, that story about Triad Systems Corporation, the idiots used to do that. A prankster applies 450 volts to an 80 microfarad capacitor and then tosses it to an unsuspecting victim. And I was the victim of those idiots a couple of times. Well, not, I think just once. It happened to me once, and then I learned. I was new. I was wet behind the ears, so I was like, didn't know those guys were idiots. Okay, the victim's finger is burned by the discharge of the capacitor through 0.200 grams of flesh. What is the temperature increase of the flesh? Is it reasonable to assume no phase change? Okay, see they're pulling in stuff you got from chemistry and maybe physics 5A. So C is the specific heat of the human body. So the cup, so the E capacitor. This is the energy stored by the. Actually, no, we're not here yet. Never mind, we're not here yet. Okay. So why were we there before we got it? I don't know. We'll figure it out. Okay, capacitors in series and in parallel. So first of all, we start with capacitors in series. Okay, that means that they make a line like that, one right after the other. The circuit goes through all 3 of them. Okay. Now here's what happens. The battery is going to take charge off of this plate right here and move it down to this plate. Okay. Now, when it took charge off of this plate, it made this plate positive. So let's say it made it plus 5 coulombs. Well, here we have plus 5 coulombs. This guy is not going to stay 0. We're going to have electrons flow up there and make this minus 5 coulombs. So we got plus 5 coulombs and minus 5 coulombs. Well, we took 5 coulombs of negative charge away from this guy, so he becomes plus 5 coulombs. Well, he's plus 5 coulombs. Now, these guys are going to come over here and make this negative 5 coulombs. Well, that left plus 5 coulombs here, which is perfect because this guy's negative 5 coulombs. Okay? Or another way to look at it, you put negative 5 coulombs on there, that's going to repel negative 5 coulombs of charge over here, that's going to go over here. In other words, there's going to be plus 5, minus 5 here, but plus 5, minus 5, plus 5, minus 5, plus 5, minus 5 here. Or whatever, plus 10, minus 10, plus 10, minus 10, plus 6 picocoulombs, plus 6 picocoulombs, minus 6 picocoulombs, plus 6, whatever the number is, it's going to be the same all the way down. Okay, so the charge is the same across all of these guys. So capacitance equals Q over V. Okay, V then equals Q over C. but the charges are all the same. So V, the total voltage, is going to be equal to the voltage across this guy plus the voltage across this guy plus the voltage across this guy. The voltages have to sum up. The book hasn't made that clear yet. When we get into resistors, then it's very, very clear. The voltages have to, it's a conservation of energy type thing. Okay, so whatever voltage we have here, okay, this guy has voltage across it, this guy has voltage across it, this guy has voltage across it. So they have to sum up to the voltage that's being applied by the battery. So the voltages are going to be equal to those three combined. The charge is all the same. So here we have voltage is going to be equal to the voltage across C1, which is Q divided by C1, voltage across C2, which is Q divided by C2, voltage across C3, which is Q divided by 3C, all the way up to however many we may have. Okay. So what we could do is factor out the Q. So V equals Q, 1 over C1 plus 1 over C2 plus 1 over C3 plus dot 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 plus 1 over Cn, however many we may have. So that means we'll say it's C series. When we're in series, oh, there's a mistake here. This is supposed to be 1 over C series. Oops. Okay, I'm going to have to fix this and upload this again. This should be 1 over CS, not CS. 1 over CS. Okay. So, yeah. This should be 1 over CS also. I didn't finish this off. Okay, so this should be 1 over CS. This should be 1 over CS. I'll tell you what, I'm going to fix it right now. So by the time you okay, I've already sent out the blast email telling you guys it exists. I have to, okay, hold on. Okay, it's 5:09, and if you, this is a note I'm about to send out to you. I'm making the video for the rest of the chapter 19 and noted an error in PowerPoint presentation and fixed it. If you downloaded PowerPoint presentation for the last couple of hours, then you want to download it again. Okay, so so here it is. Here's save right here. This means that's where it goes out to everybody. That's what I've been told, at least. It goes out to everybody. Okay. All right. So this was the problem. See, this should be 1 over CS. See, it's V equals Q over C. Okay, so I needed to put 1 over the series capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Okay, now, if we only have 2 capacitors, which is what you're going to have on exams, it becomes real easy. Just 1 over C series equals 1 over C1 plus 1 over C2. Well, I can multiply both of these by 1. I can multiply 1 over C1 by C2 over C2. I can multiply 1 over C2 by C1 over C1, because this is 1, right? You can do that. You can multiply anything by 1. We're just multiplying it by 1. So then you get C2 plus C1 divided by C1, C2, C1, C2. Well, they have the same denominator. So you can say 1 over C series equals C1 plus C2 divided by C1 times C2. Then we take 1 over both sides. Take 1 over this, we get C series. Take 1 over this, we get C1, C2 divided by C1 plus C2. So that's what you got to do for 2 capacitors in series. Okay, now in parallel, it's even easier. All right, so in this case, it's going to be the voltage that's the same. See, these guys are in parallel. That means that you have a circuit here, but then you have a separate circuit here, and you have a separate circuit here. See, up here, all the capacitors are tied together. Okay, the circuit has to go through all of them. Here, you got 3 separate circuits, okay? The voltage is the battery's going to keep the voltage the same up here. If it's 10 volts, this is all going to be 10 volts, and this is all going to be 0 volts. That means you'll have 10 volts across this guy, 10 volts across this guy, 10 volts across this guy, whatever the battery's supplying, okay? So the voltage is the same. So now we go with Q equals CV. So Q equals C1V plus C2V plus C3V plus dot dot dot, however many capacitors we have in parallel. We factor out the voltage because it's the same for both of them. For all of them, we get C1 plus C2 plus C3, so we can replace that with CP. So CP equals C1 plus C2 plus C3 all the way up to however many we have. So that would be the equivalent parallel capacitance. We just have to add them, so it's nice and easy. Okay, so this is problem 61. Okay, hold on a second. Something is. All right. Well, let's see. Okay, we're not ready to do this one, or ready to do this one. I don't know how they got. This is 58 and this is 55 in your own. Your own got it backwards? Or I got it. I don't know what's going on. All right, so this is number 58 in your own. Suppose you want a capacitor bank with a total capacitance of 0.750 farads, and you possess numerous 1.50 millifarad capacitors, okay? What is the smallest number you could hook together to achieve your goal, and how would you connect them? Now remember, we have 1.50 millifarads, we want 0.750 farads, okay? So this number is bigger than this number. So we can't hook them up in series. Why? Because you keep hooking them up in series, the total capacitance goes down. See, if you hook up two of these together, you're going to get half of this. You're going to get 0.75 millifarads. And you put another one in there, you're going to get even less than that. Okay? But if you put them in parallel, then they add together. So you got to figure out how many you can add to get this 0.750 farads. Okay? So CP, C1 plus C2 plus however many you have. So the number that we would need is the capacitance that we want divided by each individual capacitor. Okay? So we want 0.750 farads. Okay? But we only have a bunch of 1.50 times 10 to the minus 3 farads. So how many of these do we need to get that much capacitance? We would need 500 capacitors. So you go back and multiply 500 times 1.50 times 10 to the minus 3 farads, you get 0.750 farads. So we'd have to hook up 500 of these guys in parallel, and we would have an equivalent of a 0.750 farad capacitor. Okay, this is 61. This is the one I thought people wanting to turn in their worksheet had already done, but I got confused. This is on number 3, and people are talking about turning in number 2. I cannot wait till we get back to being in class. This is a lot harder doing it from home because it's so hard to keep track of what's going on and everything. All right, so I actually have this sorted out here. Okay, capacitors in series and parallel, problem 61. This circuit has 6 capacitors in both series and parallel combinations. The most you would see on a quiz or an exam would be 4 capacitors in a circuit. So what we're doing is we're flexing our muscles. We're making a really, really hard one that's way harder than what you would see. So then when you see the ones you get, you'll say, whoa, these are easy. It's kind of like you watch a baseball game if they're playing baseball anymore. But you watch a baseball game and the batter's in the on-deck circle and he puts one of those donuts, those weights on his bat. So he starts swinging his bat with this extra weight on there. Okay, and what does that do? He says, "Oh man, this is tough to swing this bat." And then he goes up to hit. He knocks the donut off, and now the bat's nice and light. Wow, this is a light bat. This is easy to hit with. So now we'll do the hard one, like the batter in the batter's box, not the batter's box, but the on-deck circle with the weight on his bat, the donut on his bat. And then when you get to the quiz, it's like being up there with a nice light bat. So you got a nice light problem. Okay, so this is way more complicated than anything you'll see. You'll see 4 at the most, but more than likely 3 in a series parallel combination. Okay, so this circuit has 6 capacitors in both series and parallel combinations. The most you would see on a quiz or exam would be 4 capacitors in a circuit. But if you understand, no, I'm not going to worry about that. Just remember when you look at this, but if you understand this one, the ones you'll see should seem easy, okay? Well, okay, so first though we got to look at this. These 2 are in series, okay? Can't do anything with this yet. He's kind of in the middle of this mess. But these 2 are in parallel. Okay. Well, we can't say this one and this one are in series because we got this guy out here too. So what we want to do is combine these 2 first and these 2. Okay. Combine these 2 and these. By the way, I'm calling this 1, 2, 3, 4, 5, 6. This is capacitor 1 all the way through capacitor 6. So C5 and C6 are in parallel. C5 and C6, they're in parallel. So all you have to do is add those. C5 plus C6 equals 0.75 microfarads plus 15 microfarads equals 15.75 microfarads. That plus that, 15.75 microfarads, right? Right. Okay. Now, C1 and C2 are in series. Woo. shoot, these two are in series. When you do this, just cross it out. Dang it. They're in series. Okay, you're going to read parallel there. I'll go up and upload. Okay, by the time you're reading this, this will be uploaded again with that. I may as well go back and make my other correction. I'll upload this again. I'm not going to send out another blast because these are, you're seeing it now, and so you can just go up. You can just go download it now. What the heck happened here? All right. We're gonna have to call this quits because I'm getting tired. I'm not thinking properly. What's going on now? Okay. All right. So these two are in series. So that means we have to use the 1 over thing. That the C12 capacitor 1 capacitor 2 equals C1 times C2 divided by C1 plus C2. That's the equation we derived up above. So you just do that. You get 2.05 microfarads. Now these two are in parallel. I mean, are in series. See if I got that right. Yeah, I got it right. Good. So they're in series, so we got to do this again. So it's C4 and the combination of capacitors 5 and 6. Okay, we just use that equation, plug in our numbers. 1.5 microfarads times 15. By the way, there's supposed to be microfarads here, but when I was doing this on this guy, I could not figure out how to get microfarads on here anywhere. So that's why they're supposed to have microfarads. I just written out the word microfarad, but that'd take a lot of space up. All right. So these two are in parallel, so we simply do this, and we end up with these three in parallel. These two are in series, so we got to do this. We end up with these three in parallel, so then we just have to add them. So we add them up. C1, C12, C3, and C4, 5, 6 are in parallel, so we just add them all up. We get 11.4 microfarads. Okay, so there is that one. Okay, then we just have to, I thought I had a better problem. Okay, this one's too complicated of a problem. I just wanted to do it for fun, but I'm going to have to come up with some other, well, I think probably in your homework you have some problems with this. Anyway, I should have done some other problems with this. Anyway, so now we're up to energy stored in a capacitor. This is the last slide. This is the end of chapter 19. Hold on, I gotta get water. Okay, now when you charge up, when you use a battery to charge up a capacitor, you're putting energy into the capacitor. The capacitor stores energy. I told you the story about the idiots who threw the capacitor. Well, what causes you to get a shock? Stored energy. Okay, if it didn't have energy stored in it, it wouldn't have the ability to shock you. So when we connected the capacitor to a battery and charge it, we are storing energy in the capacitor. The voltage across the capacitor goes from 0 volts at the beginning of the charging process to V volts at the end. That's the battery's voltage. Okay. So in the very beginning, the capacitor has 0 volts across it. We close the switch. Then over time, it charges up to our final voltage. But during that charge time, what's the average voltage? Okay, during the charge time, it wasn't V and it wasn't 0. It was a bunch of numbers from 0 all the way up to V, and it only started on 0 and ended on V. So we got to do an average. So the average would be the V plus 0 divided by 2, but 0 is just 0, so it's just V over 2. Now remember that the electric field, the energy of the capacitor, see now we got energy here, not electric field. The energy stored in the capacitor is going to be equal to the charge times the average voltage. Okay, I'm trying to remember where we covered this. The book has it at this point. Did we cover this? Anyway, so this is going to be, the energy is going to be charge times voltage. The charge stored in the capacitor times the voltage. Yeah, we think we did, because we talked about, the change. Yeah, we talked about potential energy. We did talk about this. Good. All right, remember the change in potential energy, the work done, change in potential energy. That's going to be the energy stored in the capacitor. the work done. Okay, so Q times V, average. So that's V over 2, the battery voltage divided by 2. So we get QV divided by 2. Okay, so then C equals Q over V, which means that Q equals CV, which means V equals Q over C. That gives us all these other ones we can go to. So C cap equals QV over 2. But if we want to plug this in, Q equals CV, so put in CV there, we get CV squared by plugging this in for Q over 2. And we could also plug in for V. V equals Q over C, so we'll plug in for this V, we'll plug in QC. So we get Q on the top, but it's Q times Q, so we get Q squared divided by 2C. Okay, so this is, so if you have charge or voltage, if you have two of the three, capacitor, voltage, charge, you need two of those, you can calculate the energy that is stored in that capacitor. Okay, so let's go and look at the problem. It's this guy right here. So a prankster applies 450 volts to an 80 microcoulomb capacitor. Okay, so we have the voltage, we have the capacitance, and then tosses it to an unsuspecting victim. So they use the word prankster. I like to put some other word in there, but this is a G-rated show, so I can't say what kind of word I want to put in there. That was way back in like 1915. I still remember that from what's that, like over 105 years ago. I still remember that guy did that. The victim's finger is burned by the discharge of the capacitor through, okay, this is where it kind of gets complicated, 0.200 grams of flesh. Okay, what is the temperature increase of the flesh? Is it reasonable to assume no? So you would just have to use this, okay? So what is the temperature increase of the flesh? So you've got this equation, which you probably saw in maybe in your 5A class, but definitely in chemistry you needed to see this. All right, so this is the amount of energy stored in the capacitor. This would be the amount of energy this is the amount of energy that went into the flesh, right? The mass of the flesh, which they're saying is 0.2 grams of flesh. The specific heat of humans, which is whatever the human body. What do they use? They used 3,500 joules per kilogram degrees Celsius. Okay, so you would just solve for delta T, all this stuff, and then your skin would increase by 11.6 degrees Celsius. It's reasonable to assume that they didn't vaporize your skin or even liquefy it, because you're not even close to the boiling point of whatever you would try to get to do something like that. All right. So anyway, I thought I had see, you should only have a problem when you have to do this, not this part right here. So I'm gonna have to try to come up with a problem for the next worksheet where we'll finish off chapter 19 with a couple of these kind of questions. Hold on a second. Yeah, I've got to start keeping to-do lists, so I just put that down on my to-do list for the worksheet 4. Problems, just straightforward problems. We're going to figure out energy, not problems like this. This isn't straightforward at all. All right, I think that's everything. We've covered all the slides. We've covered all of these. I think that's everything. If I think of anything else, I'll send you one of those, what they call them, flash emails, and plus, I'm gonna try to put another video up. What is today's Wednesday? Friday or Saturday? I got other classes too. I got to deal with. So Friday or Saturday, I'll try to put up another video that will cover more stuff. And if I think of anything, I'll try to remember it then. All right. So what is it now? It's 5:28. Almost time for NBC Nightly News. So I'll talk to you Friday or Saturday. I'll put out a new video. So good night for now.